The second derivative test for local extrema. Consider the graph of f of x shown. Let's plot our local extrema. Right there we have a local minimum, which we'll call local min. And over here on the right, f has a local max, or local maximum. What is true at the local minimum? Well, first of all, f is momentarily horizontal. So at the local minimum, we know that f prime equals 0. But we also see that f is concave up, which means f double prime is positive. So how do we know if we have a local min? Well, if f prime is 0 and f double prime is positive. How about at the local max? Once again, f prime is 0 because the graph is momentarily horizontal. But also, f is concave down, meaning f double prime is negative. So the second derivative test says f will have a local max if f prime is 0 and f double prime is negative. Notice that for both the first and second derivative test, we start with f prime 0, or perhaps undefined for the first derivative test. The first derivative test finishes with the first derivative, but the second derivative test finishes with the second derivative. Let's look at a few examples, starting with an algebraic one. Notice that I've given you f prime of x, which is x minus 1 times x plus 3, or x squared plus 2x minus 3. Use the second derivative test to find the local extrema of f. Even though we're using the second derivative test, since we're doing local extrema, we need to start by finding where f prime equals 0. Since we already have f prime, we can get that easily. F prime is 0 when x equals 1, or x equals negative 3. The second derivative test says, now let's finish this off with the second derivative. So we're going to find the second derivative, which is 2x plus 2. And let's find f double prime at 1, which is going to be 2 plus 2, or 4. And let's find f double prime of negative 3, which is negative 6 plus 2, or negative 4. So at both of these places, f prime is 0. Since the first place, we see that the derivative is 0, but the function is concave up, that is f double prime is positive, there is a local max. When I said max, I of course meant min. On this other one over here, where the slope is 0, but the function is concave down because the second derivative is negative, this is where we have the local max by the second derivative test. So these here, and what I call the curly brackets, or sometimes fancy brackets, these would be our justifications using the second derivative test. How about a simple numeric example? Let f be twice continuously differentiable for all x. It just allows me to do the problem. I have a nice smooth function everywhere, doubly smooth if you would. Does f have a local max, a local min, or neither at x equals 2? Well, since f prime of 2 is 0, and f double prime of 2 is 1, which is greater than 0, I have a flat function momentarily that is concave up, which means there is a local min. Pretty straightforward. One final problem. It's one of my favorite problems to give. Suppose that dy dx equals y minus x, where y of 1 equals 1. Does y have a local max, a local min, or neither at the point 1, 1. This is a second derivative test. Do not try to use the first derivative test to prove local max, local min, or neither. This is a second derivative test problem. So we're going to start by finding the derivative at the point 1, 1. Since it's y minus x, it's 1 minus 1, which is 0. So there's definitely a critical point of y, which means y potentially has a max or a min. But now we need to find the second derivative, which is the derivative with respect to x of our first derivative, recalling that notation. So we're going to take the derivative with respect to x of y minus x, which gives us dy dx minus 1. Now remember that we're at the point 1, 1. And remember that we already found that at that point dy dx equals 0, which means our second derivative at that point is negative 1, which is less than 0. Since our graph is concave down and momentarily flat, this would be the point 1, 1, we see that y has a local maximum.